Hi there, welcome back again to this course in ABE161, and this video will be moving on to our last topic for the steel structures, and that's the flexural members. Okay, so recall that a flexural member is a member loaded or having loads perpendicular to its longitudinal axis. Okay, so the load is perpendicular to this axis, and the axis of rotation would be orthogonal. Okay, so something like this. When I say orthogonal, that's going out of the page, and you'll have a pending like this. Okay, so example flexural members are beams. Okay, the most general ones probably beams and girders. And I say girders, they're flexural members that carries smaller beams, or joist. Okay, so joist usually for timber structures. If you have a narrow spaced beams, then that's gonna be a joist. Rafters. What else? We have purlins and girds. Okay, so this topic will focus on the flexural members, and we'll first discuss the preliminaries, additional topics or additional foundations that we need before we delve into the code provisions and computations. Right. So for the introduction, um, I guess it would be safe to assume that the most economical section would be the W shape or S shape. Okay, so the theory is that if we have more area away from this neutral axis, then we will have more resistance to bending. Okay, so at least this one, they are both symmetrical, and much of the area are concentrated away from this neutral axis. Whereas for channels, there's going to be some issues because of the symmetry. Okay, so it may not be as symmetric as this one. Okay, but the main principle is that I think whatever steel shape you can design it as a flexural member, provided that you are going to design that in such a way that it can carry the induced moments, and as well as the possible failures, like for example twisting under flexural loads. Some members, especially the non-symmetric, they'll be prone to some issues as compared to the doubly symmetric members. Okay, so this one we call this doubly symmetric, and this also goes through with pipes, I guess. Okay, so meaning that along this axis, then you see asymmetry, and along this axis you'll also see asymmetry. So that's doubly symmetric. But this is just singly symmetric. Okay, symmetric only along this axis. Okay, so now we'll go on to the preliminaries. Okay, so recall that when a beam is subjected to bending moments, flexural loads, the stress at any point may be computed using the Flexure formula. Okay, this is our beam. Let's say it is simply supported, and let's apply a load, a concentrated load. Okay, so because of this load, there's gonna be a bending, flexure, and if we check the section, if we cut a section, can be seen let's expose the stress distribution. We can see that there's gonna be compression. Okay, so we have a compression here and the tension, the tensile stress. And if we plot the stress diagram, so if we plot the stress diagram, we can see that we have a linear distribution. Okay, so this is compression, this one is tension. Okay, so if we increase the loads, then of course this stress will also increase, right? So you'll have more loads under the same area, and at some point it will reach the yield. Okay, so let's say this is the yield point of the material. Okay, so that's the typical elementary stress calculations for beams. But here in the steel beams, there's actually a capacity beyond this yield point. So what if we increase the load furthermore? Then you'll see that the so let's say this is the yield point. Okay, and then this one too would be the yield point. Okay, so you would notice that if you increase the load, the outer fiber of this beam reaches the yield, but the the fibers or planes closer to the neutral axis would still has not yet reached the yield point. Okay, so meaning only the outer fiber reaches the yield point. So if we furthermore increase the load, then the fiber next adjacent to this outermost fiber will then also start to reach the yield. Okay, so this will be the stress distribution. And this is what we call partially plastic. Okay, so that's beyond the elastic range, and this one is still in elastic. Okay, so if we still further increase, what we'll get is a stress distribution, something like this. Okay, so meaning that all the fibers in the beam section reaches the yield. Okay, and this is called the fully plastic region. Okay, so meaning that there is a capacity, additional capacity beyond the yield. So if we try to draw the moment diagram, diagram, you can see that for this elastic range, we can have something like this. And if we further increase the load, then we're gonna have something like this. Okay, so this one is called, this one from this point to this maximum moment, that's the moment, I think we can call it elastic moment, so m sub y, because that's the moment under the elastic region. And if you increase furthermore, there's gonna be a plastic moment capacity, so m sub p. Okay, however, within this range, if all the fiber reaches the yield point, then meaning that the section right here, let me try here, let me draw it here again. So if this, let's say this section is, if all the fibers had reached the yield point, then this point right here offers no resistance anymore to rotation. Okay, so that's gonna be something like an internal hinge. Okay, so if that's gonna be an internal hinge, then you're gonna have a failure, something like this. Okay, so this point right here, since it has reached the yield in fully plastic region, then it will fail in a way something like this. Okay, that this is something like an internal hinge. Okay, so without resistance to rotation. Okay, so there's going to be a collapse of the beam. Okay, so this phenomenon is referred to as the plastic hinge phenomenon. Phenomenon. Okay, so sometimes I'm just lazy to write. But anyways. Okay, so now let's discuss another concept. Now, what will happen if we have a beam? Okay, let's say we have a fixed end right here, and this is our beam. Say it's very long and without any support, without any lateral support here. And this is going to be, okay, think of it as a three-dimensional view, x, y, so this would be z. Okay, so imagine that we have a beam that's under a free fixed boundary conditions. This one is a free end, and this one is a fixed end. And I'm going to subject this beam under a flexural load. Okay, so imagine this is long, fairly long, and if I put a load on this edge, then the tendency of this beam is actually to twist. And it's going to be something like this. So that's going to be twisting. So let's shade the final position. Okay, so it's going to be something like this. There's a twisting. Now if we try to look at it in the zy direction, you will see that we have a twisting of the cross-section. Rotation or displacement. Okay, twisting. Okay, so from this initial position, it twisted to this position. Okay, so that's what we call twisting. Okay, so this phenomenon is called the lateral torsional buckling. Okay, this happens when you have an unbraced length. Or we can say when you have insufficient lateral bracing. Okay, insufficient lateral bracing, then that's going to be the phenomenon. It's possible that the beam will deflect in this manner. Okay, so insufficient lateral bracing, then it introduces us to the concept of unbraced length. Okay, so unbraced length is So let's say this is a beam and we have lateral supports, could be a joist or whatever, and the unbraced length is the distance, this distance without the brace. That's L sub B, or unbraced length. Okay, so how do we prevent the section from undergoing this lateral torsional buckling? Okay, so the ways, I mean, the most common ones is to provide sufficient lateral bracing. Like for example, you have to adjust the space, the brace. I mean the brace length. Another one would be to, I mean, in the case of a steel beam supporting a steel deck. Okay, so if we have a steel deck, it is something like this. A steel deck is something like a flooring supporting a concrete slab. Okay, so that's gonna be a fully braced leg. Other ones, you just have to provide additional braces here. Okay, so that's it. Now, when it comes to the shapes, there are some shapes that are susceptible to lateral torsional buckling. I'll just write a shortened way, LTB. That's that's not the food, but rather that's the lateral torsional buckling. Okay, so some shapes are susceptible, while others are not susceptible. Of course, this brace also affects this condition, but with just respect to shapes, if we have a stocky shape, that's gonna be less susceptible. And if we have, let's say, a channel and probably a deeper beam, even though it is an I-shaped beams, but if we have a much deeper beams, they are more susceptible. Okay, so this one is less susceptible, but this one would be most susceptible. Okay, so now if we graph the capacity, the moment capacity of the beam based on the plastic moment, or the moment beyond the yield point, and based on this lateral torsional buckling, you will get a graph something like this. So here, the unbraced length, and we'll have a nominal moment capacity, and we'll have something like this. So let me dark this. Okay, so meaning at some point of unbraced length, then there's going to be a lateral torsional buckling. But if you have sufficient bracing, then the lateral torsion is not an issue. Okay, so therefore, if you have this brace, this unbraced length from this point to some maximum value, then there's going to be no LTB, okay, no lateral torsional buckling. And let's denote this as L sub P. And then within this range, I mean, if you pass this unbraced length LP, and to some value, actually from this LP onwards, you'll have a lateral torsional buckling, except that there's a two types, something like two types or two regions for this unbraced length. So we have another limiting value here, L sub R, and from this range, L sub P to L sub R, we'll have an inelastic LTB. So lateral torsional buckling, but it is inelastic. Whereas this one is elastic lateral torsional buckling. This one, this curve right here, is the limiting capacity, LTB capacity. Okay, so elastic simply means that the compression flange begins to yield and then buckles. Okay, so now what is this L sub P and L sub R? L sub P can be computed using by this equation, 1.76 Ry square root of E all over Fy. So that's the L sub P. This one can be computed using the equation Lr is equal to pi r t sub s square root of E all over 0.7 Fy. Okay, and this one, this can be approximated accurately and conservatively as the radius of gyration of the compression flange plus 1/6 of the web. So it's there in the handouts. We have this equation, so that's a conservative value, square root of 12(1) plus h times the thickness of web, where 6 will be the flange times the thickness of flange. Okay, so that's the equations for this limiting case. Okay, so now let's move on to the local buckling issues. So just like the compression members, flexural members are also subjected to, or it can have a tendency for local buckling. Okay, so why? So recall that this is our beam, even though this is the flexural load. See that the stresses actually is an actual stress, right? So if we try to zoom this in, this is our neutral axis, then we'll have something like this. So you see that you'll have compression loads or actual loadings here along this region and along this region. So it is possible, I mean, it would be also common for the flexural members to have local bucklings. So therefore, we are going to check the limiting width to thickness ratio. Okay, so you already encountered this graph. We have the slenderness. I mean, we just referred to slenderness, but the more precise term would be the limiting width to thickness ratio. So we have this symbol, this lambda, and we have this this slenderness or width to thickness ratio, and we have lambda sub r over here and lambda sub p. For compression members, it's only up to here. So meaning beyond this, if you have slenderness beyond this lambda sub r, meaning that your that the element is slender. But for flexural members, there's this one comes into play, this y sub b, and this delineates whether you have a compact section and a non-compact section. It's a non-compact section, and this one would be compact section. Okay, of course, the application of this is you would actually have different different approaches for calculating the capacity of the flexural member. If you have a non-compact, or if you have a slender, if you have both compact elements for web and flange, and that's where we are going to limit our studies. We'll just limit our study, our management to this compact sections, compact web, and then compact flanges. Okay, so just a review. When we say elements, the slenderness of the elements, we have unstiffened elements and we have stiffened elements. Okay, so unstiffened is only one end is connected to, or is constrained. This one is free. So this one is the flange. And when we say stiffened elements, then both ends are restrained. An example of that is the web. Okay, so for flexural members, the value of y sub b and this, y sub b, the lambda sub b and then this lambda sub r would be different from those compression members. Now for this one, y sub b is equal to just simply the flange divided by the sorry, not that. This is 0.38 square root of e all over fy, and the y sub r is equal to one. By the way, let me write it here. Flexure in flanges of rolled high shape sections and channels. And we have our lambda here, and then this one will be lambda sub b, this one lambda sub r, and this one will be the example. Okay, so in the code, what you'll actually see is we have a case right here, and we'll only consider, for the so we'll consider case 1 and case 9. I recall that in our compression members, we have different case numbers. Okay, but in the code, there you can just find them in just one table. But the difference you'll notice here, it says here flexure and flanges. For compression members, you would see it says here compression. Okay, so that's why I only highlighted these two cases. This case 9 is flexure in webs of doubly symmetric I-shaped sections and channels. Okay, so this y sub b is 0.38 square root of e all over fy, and this lambda sub r is 1.0 square root of e all over fy. They're just basically the limiting value. So here it refers to this portion. This is the b, and take note that's the b. That's not the width of the flange, but rather it's the half of the width of the flange. Okay, so you have to take note of that. So again, this b is the distance from this point to this free end, but in the table, this b would be the flange width, meaning referring to from the distance from this point to this point. Um, by the way, I guess I don't have much time now. Then we'll continue this topic in the next video.